Okay, this chapter will specialize the results of the state estimator, the Kalman filter, to estimating kinematic models, the state of kinematic models. These are special models, and we'll see some tools to understand estimation and obtain explicit steady-state results for these situations. So what we're going to do is define a number of kinematic models, namely the white noise acceleration. Well, it's a second-order model, also called nearly constant velocity. The Wiener process acceleration, third-order model. This can be called nearly constant acceleration. And we'll derive discrete time kinematic models in two fashions: by discretizing the continuous time state space representation driven by white noise. This really builds on the developments from chapter 4. And also we'll show the so-called direct discrete time models using piecewise constant white random sequence as the process noise. And we'll see that in steady state, for noisy kinematic models, second order, we obtain what's called the alpha beta filter. Third order, we obtain the alpha beta gamma filter. And what's very important is that the gains, there are 2 gains, 3 gains here, will be expressed in terms of a single quantity that is called the maneuvering index, ratio RMS position uncertainty in motion versus RMS position uncertainty in the observation. So very simple quantity. And what we'll discuss is a couple of very important engineering ideas, how to design filter to obtain a certain level of noise reduction, whether it is possible. And also selection of the sampling frequency rate is discussed in this chapter. Okay, the discretized continuous time models. They come from kinematic motion models. Kinematic models are defined by setting a certain derivative of the position to 0. In the absence of any random input, the motion is a polynomial in time, so the position then becomes a polynomial in time, and that's why they are called polynomial models. And the filters are also called sometimes, that's not quite right, but they are, this term is used by a number of people in the field, polynomial filters. Clearly, it is not realistic to assume there are no disturbances. There's no such thing as a deterministic state model in practice. We will model the disturbances as random inputs. And the first model will be continuous time white process noise. Now, observations are done in discrete time because that's how our sensors operate. They take samples, typically, as indicated earlier, short-term integrals, but they are pretty much samples of the continuous time state. So what we need is the discrete time state equations. So the first one will be the second order in one coordinate called the white noise acceleration, 2-dimensional, and the Wiener process acceleration state model, 3-dimensional per coordinate. It should be pointed out that in many applications the same model is used for each coordinate. Each of the coordinates can be 2 or 3. In some applications, for example in air traffic control, you can use 2 third-order models for horizontal motion and a second-order model for the more benign vertical motion. There are various combinations depending on who is designing them. Another thing is across or among different coordinates, the motion is assumed decoupled. Namely, the noises, the uncertainties entering into the various coordinates are assume mutually independent. They might have different variances. Typically horizontal is one, vertical is another one. So what we are going to do is deal with such motion models in one generic coordinate. The continuous time white noise acceleration model comes from the fact that a constant velocity object moving in the generic coordinate psi is described by the equation psi double dot t equals 0. However, as I said, this is really an idealized situation. So in the idealized situation, the position psi t is a polynomial in time, in this case, second order. So this really has two coefficients, but it is a straight line. So the polynomial is really a first order polynomial, but has two coefficients. So this model, that's why it is called, it's a straight line motion, it's called the polynomial model. In practice, the velocity undergoes at least slight changes. And one way of modeling it is assuming that our psi double dot, which is the acceleration, is not identically 0, but equals to some kind of a white noise, v tilde of t, which is modeled with mean 0 and intensity that's in most cases will be time invariant. So the q tilde, the time invariant, it has the power spectral density meaning. And this will be a design parameter for the estimation filter based on this model. So in practice, you choose a model and select a design parameter based on the engineering understanding of the object whose state we are interested in estimating. And we'll discuss this in more detail later. The state vector, in this case, is two-dimensional per coordinate. Vector x will consist of psi and psi dot. And this model is called continuous white noise acceleration, CWNA, or second order kinematic model. It is really a double integrator because from psi double dot acceleration equal to 0 equal to white noise, you integrate once, you get velocity, integrate one more time, you get position. So the position really is the double integral of white noise. So the velocity in this case is a Wiener process. The continuous time state equation for the vector x consisting of psi and psi dot is x dot is axt plus dv tilde of t. A reflects with two zero eigenvalues the double integration. The position is just the integral of the velocity, and the velocity is the integral, the derivative of the velocity, that's acceleration. The second component is directly the white noise. So the two component of x tilde of x dot here is going to be the acceleration. And d being 0 and 1 indicates that the continuous time white noise enters only into the acceleration. It is the acceleration or enters into the velocity component's derivative, but it propagates via the integration from velocity to position, eventually into the position. When we discretize this state equation, we end up with xk plus 1 equal fxk plus vk. F is e to the at, and that's easy to compute transition matrix. Turns out to be 1t, 0, 1 with two unity eigenvalues in discrete time. These are the eigenvalues for integration. And the discrete time process noise relates to the continuous time according to what again has been obtained in chapter 4. Vk, this is for interval tk to tk plus 1 really, is integral 0 to t e to the a cap t minus tau. T is a sampling interval. This cap t minus tau is the time to go until the end of the interval from the moment this noise entered, and the noise enters at k cap t plus tau. So we have this transition matrix, the noise gain v tilde at the moment it enters, and tau is just the integration variable, which is from 0 to the sampling interval. Now, we had an expression for the process noise that can be used from the general expression or from this particular expression that we have the previous page. You can calculate the covariance, and after a little bit of algebra, which suggested to go through, we end up with the power spectral density of the process noise, q tilde, multiplied by t, goes into the, as a 2 term, t cube over 3, the 1 term, and there is a cross term. So you can see how the integration from velocity into position does propagate the process noise, which enters as acceleration eventually into position. Now, as indicated before, q tilde is to be selected by the designer. It's really an engineering decision that has to be made. What is the basis for this selection? Note that the changes in the velocity over a sampling period t are of the order of, that's the square root of q22. This is the difference between the velocity at k plus 1 and the velocity at k. Square root of q tilde t. This should serve as guideline for the process noise intensity choice. We choose the power spectral density q tilde for this model. Now, so it is the changes in the velocity over t. If you divide a delta v by t, that will give you an acceleration. So square root of q tilde t over cap t is approximately the average acceleration of the object over an interval. It should be noted that the physical dimension of q tilde is length square over time cube, in the metric system meter square over second cube, and a so-called nearly constant velocity model. And by the way, some people in the literature call this CV, or constant velocity model. It is not constant velocity, it is nearly constant velocity. Will be obtained by the choice of a small intensity. And what do we mean by small? The changes in the velocity are small compared to the actual velocity. Nearly constant velocity is over an interval of time. The change in the velocity, say, is 1%, 2%, 5%, something like this. This is a nearly constant velocity idea. So these are gray definitions. There's nothing hard about them. There's a lot of subjectivity, but that's the engineering art. The third order model is a continuous time Wiener process acceleration model. In this case, we start from a constant acceleration object in our generic coordinate. Either that acceleration is constant, its derivative psi triple dot is identically 0. But again, there is no such thing as perfectly constant acceleration. So what we have is the derivative of the acceleration. The jerk is modeled now as white noise. So the acceleration becomes a Wiener process. And this is why it's called the continuous Wiener process, CWPA model. The state vector for this model is three-dimensional. Psi, psi dot, psi double dot. These are the components of the vector x. And the continuous time state equation, x dot is ax plus dv tilde, has a matrix A with 3 zeros because this is a triple integrator. Again, D has a 1 in the third component. The continuous time noise enters only into the last component, the derivative of the acceleration the jerk, is white noise, but via the integration it will propagate into velocity and position. So all three eigenvalues of A, the poles of the continuous time function, are 0. So that's a triple integrator. Now, one can have other third-order models with the acceleration having autocorrelation. So the acceleration is neither white nor a Wiener, neither white noise nor a Wiener process. In between, what we have is an exponentially autocorrelated acceleration model, which is covered in chapter 8 that we probably will not have time in this course. Now, the discretized state equation for this third-order model is xk plus 1 is fxk plus vk, where the transition matrix is going to have 3 units on the diagonal. That's the triple integrator t half t square t. Clearly, this is how the acceleration becomes position, t squared over 2, how the acceleration affects the velocity multiplied by t. And we have a covariance matrix of Vk, again, a little bit of a derivation similar to what we've done in chapter 4, will give that the covariance of the discretized continuous time noise is given by the power spectral density of the continuous time noise times this matrix, and you can see again the q tilde t that enters into the acceleration, and eventually into position is a t to the 5 over 20 multiplying q tilde. Now, how to choose the process noise intensity? Again, the same engineering problem. The changes in the acceleration over a sampling period t are of the order of the square root of q33. If a random variable has a variance, in this case q33, because it is the change, the delta acceleration over an interval t, the magnitudes of that are proportional to the standard deviation. So that's why they are proportional to the square root of q33, which is square root of q tilde cap t. And remember, in this case, the units of q tilde are different than in the case of the second order model. So this will be a guideline in the process noise intensity choice. We choose the power spectral density q tilde of the continuous time noise v tilde to tune this model to the actual motion of the object of interest. Q tilde would be, for the result to be acceleration, given in units of length square, and in order to get time square here, I need time to the power minus 5. So divided by time to the power 5 multiplied by t is divided by time to the power 4, square root is time square. So the units here are meter square over second to the power 5. Now, what is a nearly constant acceleration model? A small intensity, and what do we mean by small for q tilde? The changes in the acceleration, which are the order of q tilde t square root of it, over an interval t, should be small relative to the acceleration level. And what do we mean by small? Again, a few percent. Perhaps 5, 1, 5, 10, something like that.